Hello and good afternoon, everyone. Welcome to this week's Zoom for Thought talk, during which Jason Moneill will tell us about how to go to the gym consistently for 2 weeks. Take it away.
Well, thank you for the kind introduction. And unfortunately, I've already failed the going to the gym for 2 weeks. But today we're going to be talking about a different kind of New Year's resolutions. And in order to start talking about resolutions, I need to first figure out how the pointer works. I need to introduce a bunch of other results in combinatorics. Sorry, Vaki. And hopefully some of those results will slowly connect together, and the conclusion the final boss in all these results will be these things called complete resolutions. So this is New Year's resolutions. It's a new year. It's a new me. And we're going to start by doing some of our past year's Zoom for Thought talks. So we're going to talk a little bit about some stuff in graph theory, in particular perfect matchings and bipartite graphs. And then we're going to talk about decomposing the complete graph into these perfect matchings. And then we'll get to the meme of me and Steiner triple systems. So these are an object we're going to study. And there's also a more general Steiner system with parameter K and T. And then after we've introduced all of the stuff from 1 through 4, we'll get to talk about what a complete resolution is in combinatorial design theory. And that'll be kind of the highlight of the talk and the joke of New Year's resolutions. Okay. So we're going to start by introducing a problem in graph theory about whether or not there exists a perfect matching for a bipartite graph. So bipartite graph just means we can bipartition the vertex set into 2 sets. And every edge consists of exactly 1 vertex from one of the sets and exactly 1 vertex from the other set. So up top here, we have a bunch of Zoom for Thought speakers. And down below, we have Sam's bad math puns. So there are a couple of things to note. One, a Zoom for Thought speaker is definitely not a bad math pun. So it's not like there's any intersection between these 2 sets. So it is indeed a bipartition. And the other thing to note is we actually have 12 dots in the Zoom for Thought speakers because you can never have too many Zoom for Thought speakers. So those of you who haven't signed up yet, please do. And the setup is each Zoom for Thought speaker, maybe this guy right here, will appreciate or at least be satisfied with some collection of Sam's bad math puns. So maybe this speaker will like that one and that one and that one. So that speaker thinks highly of you, Sam. And we do this for each of these Zoom for Thought speakers. And so we end up with a bunch of these lines. And the goal for each S in my Zoom for Thought speakers, Zoom for Thought. So for each of these blue dots, we want to find a unique joke J in Sam's bad math puns where SJ is an edge in whatever graph this is, edge in the graph. So at the end of the day, we want to have, let me find a new color we want to have 12 of these lines like this. So given that goal, you might ask, when can we find 12 of these lines? So when can we find a unique joke or a unique bad math pun that Sam writes for each of the 12 Zoom for Thought speakers? And the first thing you might think is, what possibly do we need? So an obvious thing is if I have one speaker, maybe that's me right there. Actually, no, I'm week 2, so I'm that guy right there. And if I don't like any of Sam's bad math puns, there's no way I could ever find a perfect matching. There's no way I could ever find a unique one for each guy because, well, there's nothing that links to me. And more generally, let's say I have the week 3 through week 6 speakers in the Zoom for Thought schedule. What do I need for their neighborhood? Or so what do I need for the collection of jokes that at least one of them finds funny? So in graph theory, we denote for a set of vertices, the neighborhood of that set to be the collection of vertices for which there exists an edge between one of them and the other. So if I look at this speaker, let's see, for week 3, I look at all their jokes. Maybe it's these ones. And I look at the speaker for week 4, so on and so forth. The neighborhood of S is just going to be the union of all of the edges that start with one of these ones, or that include one of those. So I have the neighborhood down here. And if you think about this for a minute, you'll realize that the size of the neighborhood of S has to be at least as big as S. And the reason is, if I want the end goal of having, one joke for each speaker, then I need to have at least as many things down below as I do above for each possible subset. So this condition for each subset is indeed necessary. So for each subset of Zoom for Thought speakers. So I need that condition for there to exist a perfect matching. And it turns out, theorem Hall, who actually proves something slightly more general, that this is also sufficient. Okay. So this is something that you might see in an undergraduate graph theory class. But the idea is we have some combinatorial object, which we hope exists. And there's some relatively straightforward necessary condition. And it turns out that that necessary condition is sufficient. So we're going to explore another such problem that has that phenomenon. All right. So what I want to do now is I want to write the edge set of the complete graph Kn into an edge disjoint union of perfect matchings. So before I get too much into that, what is Kn? So I've said the complete graph. So this consists of n vertices. And in this case, I'm going to let n be equal to 4. And I want every single edge, so every single pair of vertices, all 6 of them, I want that edge to be there. So this is K4. And you could also have K3. And I'm not going to draw K5, but so on and so forth. You can have all of these. And what I want to do is I want to write the edge set of this graph as a disjoint union of perfect matchings. So what is a perfect matching? A perfect matching is a collection of pairwise disjoint edges whose union is the vertex set. So what I want to do for 4 is I want to find, let's see, here is in blue, this is a perfect matching. The 2 edges span the vertex set and they're pairwise disjoint. In red, I have another perfect matching. Now I have to get a new color. I'm going to pick green. Wait, no, I don't know if that's green, but anyways, that is another perfect matching. And so what this shows is it shows that I can decompose K4 into 3 perfect matchings. Okay. And so now I have a question for someone not named Sam. And I'm going to check the chat really quick. Okay. Nothing too relevant. So question for someone not named Sam. Can I do this for K5? Oh, there's someone said something in the chat. Yes. Okay. Well, so so the answer is actually no. So for K5, let me draw a picture. We have 5 vertices. They form maybe like a pentagon like this. And I cannot find actually a single perfect matching. So maybe this vertex goes here, this vertex goes here, and there's no way to get the union of edge disjoint sets to be all of a set of size 5. So it's yeah, kind of a trick question. But in order for one of these perfect matchings to exist, the number of vertices has to be even. So what's the necessary condition necessary for problem? N has to be even. And you might have guessed that this is actually also sufficient. Yeah. So, okay. What do we want to do? We want to write the edge set of the complete graph on an even number of vertices in terms of an edge disjoint union of perfect matchings, which I denote P of M. I don't know if that's standard or not. So another way of saying this is I want to color all pairs of, let's just say the first 2n positive integers into some number M of colors where the ith color avoids this. So another way of saying that is if avoiding this means that each color class is a perfect matching if you get the numbers right. So what does that mean? Let's see, where blue. So how many edges are there in the complete graph on 2m vertices? Well, this is equal to, we have 2m choices of 2m total vertices, and we need to choose 2 of them. So this is 2m choose 2. And each choice of 2 defines an edge in the complete graph. And this fortunately has a nice formula, 2m minus 1 over 2, which, oh, oops, that's supposed to be an n. 2n, n times 2n minus 1. And each perfect matching, size of perfect matching. So if I have a perfect matching on 2n vertices, the number of edges has to be exactly half of that, which is n. So if I have any hope of doing this, we need the number of colors, m, to be 2n minus 1. Because I want m times this to be equal to that. Okay. So the problem, we've now restated it in terms of coloring each edge of the complete graph into 2n minus 1 colors. So we're coloring the edges so that each color class is a perfect matching. Okay. So we can do that. So what I'm going to do is for each pair of vertices, which does not contain the biggest vertex labeled 2n, I'm going to define the color of that pair to be I plus j mod 2n minus 1. So I'm doing everything modulo 2n minus 1. And now, what's the claim? The claim is we don't have anything that looks, so far, we don't have anything that looks like this in the same color. So why do we have that? Well, so far we're good because 2 plus 5 mod, what is this? I guess 5 is not equal to 2 plus 4 mod 5. So far we've avoided 2 edges which meet at a vertex in the same color. But we haven't colored every single edge. So the edges we have not colored look like 1 goes to 6, 2 goes to 6, 3 goes to 6, 4 goes to 6, and 5 goes to 6. So the only thing, so let's just stick with 2. What should we color? 2 goes to 6. So 2, what should the chromatic, whatever, the function of 2, 6 be? So it is going to be either 1, 0, 1, 2, 3, or 4.
Why not 5?
Because I chose to represent z mod 2n minus 1z by starting with 0.
Oh, I see.
So we want 5 colors.
I see. Okay. Cool.
So that, let me oh. All right, let me draw this out. So the edge consisting of 1 and 2, we're going to color that 3. The edge consisting of 2 and 5, that's going to be 2. 2 and 4 is going to be 1. 2 and 3 is 0. So we're going to color, oh, that got kind of messed up. But 2 and 6, we have to color it 4. And you can check that in general, you should color I with 2n to be equal to 2i. Why is that? Well, the only way you can get 2i from I is I plus I. But this is a simple graph, so we don't have edges with themselves. So you can kind of run through the details, and we take the complete graph on 2n vertices, and we color each edge into 2n minus 1 colors, where each color class is going to be a perfect matching. So when n is even, we can we can decompose the complete graph into perfect matchings. Okay. Before I go further, are there any questions? Okay. So it's another case where you have, once you understand the question, a relatively straightforward necessary condition, which is also sufficient. The next thing we have is what's called a Steiner triple system. So I'm going to have to explain some of the notation. But what we are going to consider is we're going to consider size 3 subsets of the first n positive integers. And so we're going to denote that collection as brackets n choose 3. We use that notation because there are exactly n choose 3 such size 3 subsets of that n element set. And I'm going to call a sub collection of those triples to be a Steiner triple system, which we're going to denote by SN32, if each pair, so 2 element subset, appears in exactly one of the sets in my collection. And one such example of a Steiner triple system is the phonoplane. And so the way in which you can read that is between each pair of points in the phonoplane, there exists exactly one triple or exactly one line which contains those 2 points. So the phonoplane is a finite geometry consisting of points of lines, where between any 2 points, there is exactly one line. And so this Steiner triple system, in some sense, generalizes that phonoplane because for each pair of points, there's exactly one triple in your collection which contains it. So as you may guess, the natural question is, for what values of n do there exist Steiner triple systems? So the phonoplane shows that when n equals 7, there are Steiner triple systems. And now what we're going to do is we're going to look at a necessary condition for the existence of a Steiner triple system. So what I'm going to do is I'm going to take an arbitrary triple. So it might look like a triangle like this. So this is some S. No, I'm going to call it T for triangle. This is some triangle in my collection. So I'm supposing there exists such a S. And I'm going to take such a triangle. And for each triangle, I'm going to look at the 3 subedges. So this is some subedge, maybe E1. This is a subedge E2. And this is another subedge, where by edge, I mean size 2 subset, which I guess also is consistent with the geometry meaning. And now what I'm going to do is I'm going to sum over all possible of all sets in my subcollection. And I'm going to do an analysis trick. Vaki, I hope to get your attention. Analysis trick with indicator functions or whatever. So I'm going to take, so this is going to end up being, okay, so for each subset T in my collection S, I'm going to look at how many times I'm going to have an edge triangle incidence pair. So in words, I'm going to sum over all possible edges. And I'm going to look at the indicator function of whether or not that edge is contained in the triangle. And so each time I have a size 3 subset, I'm going to get a contribution of 3 to this sum, because each triangle T has exactly 3 edges, size 2 subsets. So on the one hand, this is equal to 3 times the size of S, which, being somewhat lazy, is denoted in 3, 2. So on the one hand, it's 3 times the size of S, but the other hand, you can do Fubini-Tonelli, which is not really Fubini-Tonelli, but change the order.
I need you to verify that those measure spaces are sigma finite.
So I can change the order, and I'm going to sum over each edge, and then each triangle, and this looks more complicated than it actually is, because what's the condition? Each pair or each edge is contained in exactly one subset. So this kind of annoying looking thing is just a fancy way of writing 1. So we actually get sum of, and then 1, which is another way of writing n choose 2. So the necessary condition, if one of these Steiner systems exists, Steiner triple system, we need the size of S to be exactly n choose 2 over 3. This is not always an integer. So this is an integer if and only if n is equal to 1 or 3 mod 6. I think you might have to be a bit careful when n equals 1. So hopefully I've convinced you that it is necessary for n to be 1 or 3 mod 6 in order for these things to exist. And I won't prove it today, but it took 3 papers to actually show that this is indeed sufficient. So these Steiner triple systems exist when n is 1 or 3 mod 6. And I will actually construct 1. So I'm going to take the vector space f2 to the n, and I'm going to throw out the 0 vector. So I have 2 to the n minus 1, and you can actually check that this is in 1 or 3 mod 6 of these points, and my collection of triples will correspond to solutions to the equation x plus y plus z is the 0 vector. And so in order to show that this is a Steiner triple system, I need to convince you for each pair, for each distinct x and y in my vector space, there exists a unique, technically it's x, y, z, but x and y are sort of implicit, such that x plus y plus z is the 0 vector. And turns out all you can do is take z to be actually x plus y because it's characteristic 2. And that is the unique solution. So that is a linear algebra construction of one of these Steiner triple systems, which takes care of some values of n for whether or not these things exist. Okay. Now I'm going to move on to a more general Steiner setting. So before we had parameters for the second input equal to 3, and then the third input equal to 2. Now I'm going to have a more general input k and input t, but the idea is very similar. So what I want to do is I want to look at size k subsets of brackets n. And the notation we use for that is brackets n choose k. For the same reason, there's exactly n choose k of them. And a Steiner system SNKT is so that each size t subset appears in exactly one of the sets from my collection. So I have another question for not Sam. So I guess the question is, what is SN to 1? And have we seen it before? So in this notation, I want each size 1 subset to be contained in exactly one size 2 subset. And I should probably check the chat. Oh, not Sam is ready. The prime ministers. Yeah, that's exactly correct. It is indeed the prime ministers. It's a perfect matchings. So before we had these graph theoretic perfect matchings, which consist of edges of size 2, which are pairwise disjoint, and the union of those edges is every single vertex, so size n. So that's what that is. Before we were just talking about SN32, and so this more general KT setting has a lot of similar flavors. So what I can do is I can go back to this handshake lemma argument. So let's see. And I'm going to use the fancy tool, copy. And oh man, hopefully this paste. Let's see, paste. Yeah, I think I got that. Okay, so now I'm going to slightly alter the argument to get a necessary condition. So what I'm going to do is now instead of summing over all pairs, I'm going to sum over all t sets, and now I use bad notation. Okay, let's see. So I'm going to sum over all size t sets, call them t, and then I'm going to sum over all sets S in MathCal S, and I'm going to look at whether or not my size t subset is contained in my size k subset. So that's going to change to this. So T, the indicator is T is a subset of S. I'm still summing that. That should be a T. That should be a lowercase t. That should be a T. So the final thing we end up with is going to be n choose T. But this thing in front here is no longer 3. So for each size K subset, we might have, this is a size K, size K, so set of, S is K. I'm summing over all size T subsets of that K element set. So we should actually get K choose T. Okay, what's the conclusion? The conclusion is K choose T times the size of your collection should equal n choose T. So let's see, what do we need? We need K choose T times the size of my collection of size K subsets better equal n choose T for one of these things to exist. So in words, that means that K choose T should divide n choose T. And it turns out you can actually look at smaller subsets and get some more divisibility conditions. So I need K minus 1 choose T minus 1 to divide n minus 1 choose T minus 1, so on and so forth. But yeah, okay, so there's more divisibility things that you need in order for this to be true and to exist. And a few years ago, this was shown to be sufficient. Immediately corollary, define 3 to be.
Most of the chat is garbage. I just mentioned earlier in the talk. I just mentioned earlier in the talk that the thing I have learned from this talk is that in combinatorics, every necessary condition is immediately also sufficient. So that's why it's an immediate corollary.
But wait, this condition isn't sufficient in general.
For the existence of Steiner systems?
Right? Because don't you need n sufficiently large?
Oh, okay, yes.
Oh, damn.
So what's best known is this is only good enough for n sufficiently large.
And there are genuine cases where, like, for small n, this is not sufficient. Like there are.
Yeah, but yeah. Okay, so for n large enough, these are sufficient. So now that we've talked about more general Steiner systems, we can actually talk about what a complete resolution is. But first, probability aside, it turns out even when there does not exist a Steiner system, we can find an approximate Steiner system. And so what this is it is a collection of size K sets close in size to that of a Steiner system. But each size T subset is contained in at most 1 set from my collection. So either 0 or 1. And you can do this for n sufficiently large, but any n, no matter what the divisibility conditions are. So this is called the Rootal Nibble. I won't talk too much about it, but turns out you can do pretty well if you only care about, getting a large thing that has a very similar property. Okay, so what is a complete resolution? So before we are looking at brackets n choose K, and we're considering subsets of brackets n choose K. But what we're going to do here is we're going to consider the whole set. So the collection of all size K subsets of the first n positive integers. And now what I want to do is I want to write brackets n choose K as an edge disjoint union of Steiner systems corresponding to parameters n, k, and k minus 1. each of these Steiner systems, I then write as an edge disjoint union of Steiner systems with parameters n, k, k minus 2, so on and so forth. So these were also shown for n sufficiently large to exist, provided some divisibility conditions hold. So that's a complete resolution. The paper is incredibly complicated. So maybe a New Year's resolution would be to understand it. But in the case when k equals 2, what is this? Well, this is writing. So when k equals 2, k equals 2, I want to write brackets n choose 2 as an edge disjoint union of Steiner systems to 1, which Greg appropriately noted where each of these n to 1s is actually a perfect matching. Let's see. So this is the same as what we did before with the perfect matchings. So this more general complete resolution is the k uniform extension of the coloring the complete graph kn in terms of where each color class is a perfect matching. So maybe I'll say a bit about when k equals 3. There's a kind of interesting story. So there was an author in the 80s and 90s in a series of 4 to 5 papers established that complete resolutions exist when k equals 3 for all values which for all the necessary values of n, except for like a list of like 7. And then someone else came along and reduced that to 4. And finally, in 1992, I believe, it was resolved for the remaining 4 values in a paper, which I think was longer than the union of everything that's been done before.
Math is so dumb.
So a lot of people worked really hard on these things. And the case where k equals 3 came up in something I was working on. And this was around a year or so ago. And I learned about complete resolutions. And at that time, I told Sam, hey, I have an idea for a Zoom for Thought talk that people might find somewhat interesting. And I slotted out a time in the beginning of the new year. So that's the story behind.
So you were completely resolved to tell us about the resolution to the complete resolution problem.
I couldn't have said it better myself.
I would argue that you should cite me, Vaki, for that joke.
True. Inspired by ideas of Spiro.
Thank you.
Oh, I see. Yeah.
We're working on a
we have
series
that
of 6 papers to explain that joke. All right, I'll stop being an ass. Are you?
Yeah,
is that the end?
I am now done for the talk. Thank you guys for listening. I hope this was at least somewhat interesting and it met the necessary requirements for a Zoom for Thought talk.
Very good. Therefore, it is also
sufficient. Yeah.
Let us thank the speaker. Any questions? I have a question.
Yeah.
How big does n have to be in terms of k? I love asking those questions.
I'm not entirely sure. Yeah, so this paper of Kivosh is from 2014, and then there's like a second version from 2018. I think the first version is 75 pages and the second one's in like 60 pages or so. And it's really involved. So probably incredibly large.
Hell yeah.
And I'm not even entirely sure if anyone's worked out the details of how large it would need to be.
I don't think anyone's like totally worked out the details that it like works like 100%.
Yeah. Yeah.
Oh no.
I mean, we have 2 papers now by famous groups of mathematicians proving it. So the result is surely true.
Yeah, my understanding by reading some blog posts online, which take it as you will, is it's essentially a combination of this finding an approximate one and using very involved algebraic arguments to show that these things exist. But that was some blog post, which I don't know.
Well, I think the blog post was also by Gowers, so I think it's fair to.
Okay, maybe I'm thinking of another blog post, but
maybe.
Okay, if it's by Gowers, then it's probably also reasonable.
Amazing. Any other questions? All right, let us thank the speaker once more.